Sodium is a highly reactive metal. You throw a piece of sodium into water, it will explode. Chlorine is a poisonous gas. It was used as a chemical weapon in the First World War. But when sodium reacts with chlorine, we get a compound called sodium chloride that we eat every day. This is common salt or table salt. We don't like our food if this is missing in it. This is a chemical reaction and it is represented by using the names of the substances involved in the reaction. But it would be more convenient if we can represent a chemical reaction using symbols and formulae instead of names. Sodium is a metal and it is monoatomic. That is, it is composed of atoms, so it must be represented by its symbol Na. This symbol represents that the element is sodium, and it also represents exactly one atom of sodium, not any random amount of sodium. Chlorine is a molecular substance. It is composed of diatomic molecules, and this is the molecular formula of chlorine. And the chlorine used for this reaction is composed of molecules, so it must be represented by its molecular formula Cl2, not by its symbol Cl. Again, this molecular formula represents that the element is chlorine. It also represents exactly one molecule of chlorine. Sodium chloride is an ionic compound, and this is the formula of sodium chloride. It is composed of sodium ions and chloride ions. This formula represents the smallest unit of this compound. That is why this is called formula unit. Remember, ionic compounds do not contain molecules. Again, this formula represents exactly one formula unit. And if you represent a chemical reaction using symbols and formulae, it is called a chemical equation. Remember, as we discussed before, atoms of each element are conserved in a chemical reaction. That is, the total number of atoms of each element must be same before and after the chemical reaction. But here on the left hand side we have two chlorine atoms, but there is only one chlorine atom on the right hand side, of course in the form of a chloride ion. So chlorine atom counts are not matching. To match chlorine atom counts, can we change the subscript of chlorine in this formula? No, we should not do that. Changing subscript of an element in a formula means changing the composition of the compound. Composition of a compound is constant. Remember law of constant composition. Therefore, to match atom counts, we can never change subscripts. Then how do we tally atom counts? To do that, you can only change the coefficients in the equation. We can put a 2 before this formula. Now we have two chlorine atoms, but we also have two sodium atoms. But on the left hand side there is only one sodium atom. So now sodium atom counts are not matching. To match them, can I change the subscript to Na2? No, we can never change subscripts. we can only change the coefficients. So we can put a 2 here. Now sodium atom counts are matching, chlorine atom counts are also matching. Now we call this equation balanced. This is a balanced chemical equation. Now I want to conduct this chemical reaction. To do that, I have to go shopping for some sodium and chlorine. See, if all I want to do is to carry out this reaction, I will buy some amount of sodium, some amount of chlorine, then we will get some amount of sodium chloride. Probably some sodium or chlorine will be left behind, and that might get wasted. But if you want to conduct this reaction without wasting any sodium or chlorine, that is, if I want to convert all the sodium and chlorine that I buy into sodium chloride without any leftovers, then we need to know in what amounts we must buy sodium and chlorine. So somehow we have to figure out the quantities of sodium and chlorine that combine completely with one another without any leftovers using this balanced chemical equation. By the way, what information do we get from a balanced chemical equation? See whether the equation is balanced or not. We can always see what the reactants are and the products are from a chemical equation. But in a balanced chemical equation, we also see some numbers before the symbols and formulae. If you do not see any number before a symbol or a formula, you have to imagine a 1 there. The numbers we see before the symbols and formulae in a balanced chemical equation are known as stoichiometric coefficients. But what information do these stoichiometric coefficients give us? Let us see. We said the symbol Na represents exactly one sodium atom. If you put a coefficient 2 before it, it represents 2 sodium atoms. Obviously, one Cl2 represents one molecule of chlorine, and 2 NaCl represents 2 formula units of NaCl. Now read this line. It says 2 atoms of sodium combine with one molecule of chlorine to form 2 formula units of NaCl. Does it mean then to carry out this reaction I must combine only 2 sodium atoms with one molecule of chlorine? No, that is not what it means. It says for each molecule of chlorine there must be 2 sodium atoms. This tells the relative number of sodium atoms and chlorine molecules that are participating in the reaction. It says the number of sodium atoms and chlorine molecules must be in the ratio of 2 to 1. That is, in the ratio of their stoichiometric coefficients, so that there will be no wastage. Okay, good. Let us go shopping for some sodium and chlorine. All we have to do is buy sodium atoms and chlorine molecules in the ratio of 2 to 1. So if we buy n chlorine molecules, we have to buy 2n sodium atoms. But nobody will be able to help us because there are no particle counters in these shops. We cannot count particles like sodium, atoms and chlorine molecules. So we cannot buy sodium atoms by count. We cannot buy chlorine molecules by count. We can buy them only by weight. We can buy certain mass of sodium and certain mass of chlorine. Now let us say we wanted to buy apples and oranges in the ratio of 2 to 1. That is, for every orange that I buy, I want to buy 2 apples. So this is my goal, to buy them in this ratio by count. But let us say the fruit vendor does not sell them by count. She sells them only by weight. So I can buy certain mass of apples and oranges, not certain number of apples and oranges from her. So now we have to figure out the weights of apples and oranges that contain apples and oranges in this ratio by count. See, my goal is to buy them in this ratio by count, but because she is not selling them by count, I am forced to buy them by weight and figure out the weights of apples and oranges that I must buy so that I will have them in this ratio by count. We have the same problem here. This equation tells that if the sodium atoms and chlorine molecules are present in the ratio of 2 to 1, then they would completely combine without any leftovers. But because these particles are extremely tiny, we can neither count them nor no amount of time will be sufficient to count them. Even a small sample of sodium would have such a large number of atoms. So we cannot count sodium atoms and chlorine molecules. So we cannot buy them by count of particles. We can only buy them by weight in kilograms, in grams, etc. So now we have to figure out the weights of sodium and chlorine that contain sodium atoms and chlorine molecules in this ratio, if you don't want to waste any sodium or chlorine. And we have discussed a similar problem earlier. Do you remember that? If needed, kindly go back and watch that part. I will quickly remind what we discussed back there. We imagined a fruit shop that sold different types of fruits, and fruits of each kind are identical. All apples are identical to one another, all oranges are identical to one another, and so on. And our goal was to buy different kinds of fruits in equal number whenever we visited this shop. We were not worried about what that number actually was. As long as we have them in equal number, we were happy. To be able to do that, we said we need the relative mass of a fruit of each kind. But we were not allowed to use a kilogram weight or a pound weight as a reference to determine their relative masses. Then we understood that actually the reference does not matter. Therefore, we said we can as well use the mass of a grape as a reference to determine the relative masses of different kinds of fruits. So we took the mass of one grape as reference and figured out the relative masses of different fruits. Then if the quantities of different kinds of fruits that we buy are in the ratio of their relative masses, then we are guaranteed to have equal number of fruits. What is the ratio of the relative masses of an apple, an orange and a mango? 200 to 250 to 350. So that is 2 to 2.5 to 3.5. So if I buy 2 kilograms of apples, 2.5 kilograms of oranges and 3.5 kilograms of mangoes, because the ratio of these weights is equal to the ratio of their relative masses, we are guaranteed to have equal number of fruits in these quantities of apples, oranges and mangoes. As simple as that. Similarly, if you buy 4 kilograms of apples, 5 kilograms of oranges, 7 kilograms of mangoes, again you will have equal number of fruits of each kind, because the ratio of these weights is again equal to the ratio of their relative masses. We are in a similar situation with atoms. We have different elements like oxygen, nitrogen, sulfur, chlorine, etc. just the way we have different types of fruits. And atoms of a given element are all identical, just the way we imagined that fruits of a given type are all identical. But you may say atoms of a given element are not actually identical if it has multiple naturally occurring isotopes. That is true. But remember, we imagine that the element is actually composed of these imaginary average atoms, though it may actually be a mixture of atoms of different isotopes of that element. Therefore, we can say that atoms of an element are all identical to one another if you take the average atomic weight of that element. Now our goal is to buy equal number of atoms of different elements. Then how can we do that? Same thing. You need the relative atomic masses of different elements or atomic weights of different elements. But we cannot use a kilogram or a pound as the reference to determine these relative atomic masses. The first problem is atoms are too small, so you cannot weigh them using these big references of mass like a kilogram weight or a pound weight. Secondly, even if you could, the relative mass of these atoms would be very small, and such small numbers are inconvenient. But as we discussed in the case of fruits, it does not matter what our reference is. So we said we take 1/12 of the mass of a C12 atom, that is one unified atomic mass unit, as the reference, just the way we took the mass of one grape as the reference to determine the relative masses of these fruits. So using this mass as reference, we determine the relative atomic masses of various elements using a mass spectrometer. So mass spectrometer is a kind of balance that we use to compare the masses of different atoms with 1/12 of the mass of a C12 atom. and here are the approximate relative atomic masses or atomic weights of some elements. Now, if I want to buy equal number of oxygen atoms and chlorine atoms, what amounts of oxygen and chlorine should I buy? Simple. The weights must be in the ratio of their atomic weights or relative atomic masses. This is the ratio of their atomic weights. So, if you buy 16 grams of oxygen and 35.5 grams of chlorine, then you are guaranteed to have equal number of oxygen atoms and chlorine atoms. Or you could buy 16 kilograms of oxygen and 35.5 kilograms of chlorine as well. These weights are also in the same ratio. So these amounts of oxygen and chlorine will also have equal number of atoms. Or 16 pounds of oxygen and 35.5 pounds of chlorine would work as well, because their ratio is same as the ratio of their relative atomic masses. So, to get equal number of atoms of different elements, the weights of those elements that you buy must be in the same ratio as the ratio of their relative atomic masses or atomic weights. As simple as that. Okay, now let us say we want to buy equal number of atoms of all elements. Now, in what quantities must we buy them? One option is take atomic weight of each element and simply add the unit gram. That is, take 16 grams of oxygen, 14 grams of nitrogen, 32 grams of sulfur, 35.5 grams of chlorine, 52 grams of chromium, and so on. The second option is take the atomic weight and add the unit kilogram. 16 kilograms of oxygen, 14 kilograms of nitrogen, and so on. The third option is 16 pounds of oxygen, 14 pounds of nitrogen, and so on. As long as these ratios are equal to the ratio of their atomic weights or their relative atomic masses, we are guaranteed to have equal number of atoms. So if you take the first case, what are we doing here? Take this 16 grams of oxygen. Atomic weight of oxygen is 16. So we took 16 grams of oxygen. So we simply added the unit gram to its atomic weight or relative atomic mass. Now, to represent this particular amount or mass of oxygen, let us create a name by adding the word gram to the left hand side as well. Then it becomes gram atomic weight. So, gram atomic weight represents a particular mass of an element that is equal to its atomic weight or relative atomic mass expressed in grams. Atomic weight of chlorine is 35.5. So gram atomic weight of chlorine is simply 35.5 grams of chlorine. Atomic weight of nitrogen is approximately 14. So 1 gram atomic weight of nitrogen is simply 14 grams. So gram atomic weight represents certain mass of an element. that is equal to its atomic weight in grams. Now, if you feel gram atomic weight is too long, you can drop this word completely and these two letters as well. So it becomes gram atom. So gram atomic weight and gram atom are one and the same. Simply put, it is the atomic weight of an element in grams. Remember, gram atomic weight and gram atom represent certain mass of an element. Similarly, what do you call 16 kilograms of oxygen? If atomic weight expressed in grams is gram atom, atomic weight expressed in kilograms obviously would be kilogram atom. Similarly, 16 pounds of oxygen is pound atom. Pound atom is atomic weight expressed in pounds. Now, here are certain molecular substances, and these are their approximate relative molecular masses or molecular weights when determined using 1/12 of the mass of a C12 atom, that is 1 U, as the reference. Now I want to have equal number of molecules of these substances, not atoms, molecules. Then in what quantities should we buy them? Again, the logic is same. If you want to have equal number of molecules of these substances, then the quantities must be in the ratio of their molecular weights or relative molecular masses. So one option is to take 32 grams of oxygen, 28 grams of nitrogen, 16 grams of methane, and so on. Second option is to take 32 kilograms of oxygen, 28 kilograms of nitrogen, 16 kilograms of methane, and so on. The third option is 32 pounds of oxygen, 28 pounds of nitrogen, 16 pounds of methane, and so on. Now, what do we have here? 32 grams of oxygen. Molecular weight of oxygen is 32. So, we took 32 grams of oxygen. So, we simply added the unit gram to its molecular weight or relative molecular mass. To represent this particular mass of oxygen, let us create a name by adding the word gram to the left hand side as well. Then we will have gram molecular weight. So gram molecular weight represents a particular mass of a substance, a molecular substance, that is equal to its molecular weight or relative molecular mass in grams. Because molecular weight of oxygen is 32, 32 grams of oxygen is 1 gram molecular weight. Obviously, this name is very long. So let us shorten it. We can drop this word weight altogether and change this word molecular to molecule. So gram molecule and gram molecular weight are one and the same. Simply put, molecular weight of a molecular substance in grams. Okay, some of us may feel even gram molecule is long, so they said drop these 4 letters and simply call it gram mole. So gram mole, gram molecule, gram molecular weight mean the same. Molecular weight in grams. Okay, if you feel even gram mole is long, drop this word gram altogether and simply call it mole. Okay, finally, the lead character of our story appears. Mole. So, mole, gram molecule, gram molecular weight mean the same. Molecular weight of a molecular substance expressed in grams, simply put. So, mole represents a particular mass of the substance. And here are some ionic compounds and their approximate formula weights. Again, if you want to have equal number of formula units of different ionic compounds, then their weights must be in the ratio of their formula weights. The formula weight of sodium chloride is 58.5. So if you take 58.5 grams of sodium chloride, it is 1 gram formula weight of sodium chloride. So gram formula weight is nothing but formula weight of an ionic compound in grams. Similarly, here are some ions and their ionic weights. To have equal number of ions of different types, the weights of those ions must be in the ratio of their ionic weights. The ionic weight of sulfate ion is 96. So if you take 96 grams of sulfate ions, we have to add the word gram to the left hand side as well. It becomes gram ionic weight or simply gram ion. Gram ion and gram ionic weight are one and the same. Simply put, it is the ionic weight of a particular type of ion in grams. So the ionic weight of sulfate ion is 96. So 1 gram ion of sulfate ions is 96 grams. Now we know what gram ionic weight or gram ion is. We know what gram formula weight is. We know what gram molecular weight, gram molecule, gram mole or mole is. We also know what gram atomic weight or gram atom is. Now let us take 1 gram atom of different elements. Gram atom is nothing but atomic weight in grams. So 1 gram atom of oxygen is 16 grams of oxygen. 1 gram atom of nitrogen is 14 grams of nitrogen. 1 gram atom of sodium is 23 grams of sodium, and so on. Obviously, these quantities or amounts are in the ratio of their atomic weights. So they will all contain the same number of atoms. Therefore, we can say 1 gram atom of different elements contain the same number of atoms. We can say the same for 1 kilogram atom of all elements, 1 pound atom of all elements, 1 ton atom of all elements. We have so many names, but these names are not as popular as gram atom is. Therefore, we can disregard these names. Gram atom is popular because these are the kind of quantities that we deal with in our laboratories. We deal with 23 grams of sodium or 32 grams of sulfur, not 32 tons of sulfur or 23 kilograms of sodium. Now let us consider 1 mole of different molecular substances. Mole or gram mole is nothing but molecular weight of the substance in grams. So 1 mole of oxygen is 32 grams of oxygen. Remember, molecular weight of oxygen is 32. Atomic weight of oxygen is 16. Pay attention to that. Similarly, 1 mole of nitrogen is 28 grams of nitrogen. 1 mole of carbon dioxide is 44 grams of carbon dioxide, and so on. Again, these amounts or quantities are in the ratio of their molecular weights, obviously. So these amounts of substances would have the same number of molecules. So we can say 1 mole of all molecular substances contain the same number of molecules. Again, we can come up with names like 1 kilogram mole, 1 pound mole, 1 ton mole, etc. But these names are not as popular as gram mole or simply mole is. But these names are still used by some industries in different parts of the world. But we can ignore these names for our discussion. Similarly, let us consider 1 gram formula weight of different ionic compounds. We can say the same. 1 gram formula weight of all ionic compounds contain the same number of formula units. Similarly, if you take 1 gram ion of different ions, they will all contain the same number of ions. Remember, gram ion is nothing but ionic weight in grams. So 1 gram ion of sulfate ions is 96 grams of sulfate ions. 1 gram ion of dichromate ions is 216 grams of dichromate ions. Now let us say 1 U, that is 1 unified atomic mass unit, or 1/12 of the mass of an atom of C12 isotope is equal to P grams, where P is the conversion factor between unified atomic mass unit and gram. And I don't know the numerical value of P just yet. We know the relative atomic mass or atomic weight of sodium is approximately 23. And if you want to get the mass of one sodium atom or atomic mass of sodium, you simply have to add the unit U to its relative atomic mass or atomic weight. So atomic mass of sodium is 23U, and if you want to express it in grams, replace U with P grams, because we said 1 U is equal to P grams. So mass of one sodium atom is equal to 23 P grams. Or in other words, if you take 23 P grams of sodium, then you have just one sodium atom. Then if you take 1 gram atom of sodium, that is 23 grams of sodium, how many sodium atoms will be there? Let us call that number capital N. Capital N will be equal to, you have to multiply these two terms and divide that product with this term. It will be 23 grams multiplied by 1 over 23 P grams. These units get cancelled, these numbers get cancelled, and we will be left with 1 over P. So in 1 gram atom of sodium, there are 1 over P sodium atoms. But we already proved that 1 gram atom of all elements contain the same number of atoms. So if 1 gram atom of sodium has 1 over P sodium atoms, that means 1 gram atom of magnesium would have 1 over P magnesium atoms. So now we can say 1 gram atom of all elements contain the same number of atoms, and that number is equal to 1 over P, where P is this conversion factor. Similarly, we know that the relative molecular mass or molecular weight of carbon dioxide is 44. And if you want to know the mass of one carbon dioxide molecule or simply molecular mass of CO2, you have to add the unit U to its relative molecular mass or molecular weight. So the mass of one CO2 molecule is 44 p grams, because we said 1 U is equal to p grams. Or in other words, if you take 44 p grams of CO2, then you have just one CO2 molecule. But if you take 1 mole of carbon dioxide, that is 44 grams of carbon dioxide, then how many molecules would we have? Again, denote it by capital N. Then capital N will be equal to 44 grams multiplied by 1 over 44 p grams. Again, these two units get cancelled, these numbers get cancelled. Again, we are left with 1 over p. And the same as before, we proved that 1 mole of all molecular substances contain the same number of molecules. So if 1 mole of CO2 has 1 over p CO2 molecules, then 1 mole of any other molecular substance also contains the same number of molecules. So now we can say 1 mole of all molecular substances contain the same number of molecules, and that number is equal to 1 over p. Similarly, you can prove that 1 gram formula weight of all ionic compounds contain 1 over p formula units, and 1 gram ion of any ion contains 1 over p ions. So we can say number of atoms in 1 gram atom of any element is equal to the number of molecules in 1 mole of any molecular substance, that is equal to number of formula units in 1 gram formula weight of any ionic compound, that is equal to number of ions in 1 gram ion of any ion, and that is equal to 1 over p, where p is that conversion factor between unified atomic mass unit and gram. And in honor of Amedeo Avogadro, this number is named after him. It is denoted by capital N or capital N with the subscript O. It was named after him a few years after he passed away. So there is no chance that Avogadro knew the value of his number, whatever it is. Okay, here is the summary of what we have learned so far. For atoms, we have defined relative atomic mass or atomic weight. For molecules, we have defined relative molecular mass or molecular weight. For formula units of ionic compounds, relative formula mass or formula weight. And for ions, relative ionic mass or ionic weight. Remember, these are all dimensionless numbers. And here are their definitions. And relative atomic mass expressed in U is its atomic mass. Relative molecular mass in U is its molecular mass. Relative formula mass in U is its formula mass. Relative ionic mass in U is its ionic mass. And atomic weight or relative atomic mass in grams is gram atomic weight or gram atom. Similarly, molecular weight or relative molecular mass in grams is gram molecular weight or gram molecule or gram mole or simply mole. Relative formula mass or formula weight in grams is gram formula weight, and relative ionic mass or ionic weight expressed in grams is gram ionic weight or gram ion. We know 1 gram atom of any element and 1 mole of any molecular substance, 1 gram formula weight of any ionic compound, and 1 gram ion of any ion contain the same number of particles, and that is equal to Avogadro's number. And Avogadro's number is denoted by capital N or N0, and it is equal to 1 over P, where P is the conversion factor between unified atomic mass unit and gram. Now let us get back to our original equation. 2Na plus Cl2 gives rise to 2NaCl. We know how to read this equation. It says 2 atoms of sodium combine with 1 molecule of chlorine to produce 2 formula units of NaCl. So we have to obtain sodium atoms and chlorine molecules in the ratio of 2 to 1 so that there will be no wastage of sodium or chlorine. We just understood that the number of atoms in 1 gram atom of any element is equal to the number of molecules in 1 mole of any molecular substance. So if you take 1 gram atom of sodium and 1 mole of chlorine, you will have equal number of sodium atoms and chlorine molecules. So their ratio will be 1 to 1. But we want them in the ratio of 2 to 1. So we have to multiply this with 2 and this with 1. So if you take 2 gram atoms of sodium and 1 mole of chlorine, we will have them in the ratio of 2 to 1. We know 1 gram atom of sodium is 23 grams of sodium. Gram atom is its atomic weight in grams. And 1 mole of chlorine is 71 grams of chlorine. Mole is nothing but its molecular weight in grams. So if you take 46 grams of sodium and 71 grams of chlorine, you will have sodium atoms and chlorine molecules in the ratio of 2 to 1. So there will be no wastage of sodium or chlorine. Now, how do we get this line from this equation? Simple. In this equation, we have the symbol of sodium. It represents an atom of sodium. So, if you see an atom in the equation, just write gram atom here. Then multiply it with its stoichiometric coefficient. So, 1 gram atom of sodium multiplied by 2. And if in the equation you see molecular formula, simply write 1 mole of that substance and multiply it with its stoichiometric coefficient. Similarly, on this side, NaCl is the formula unit of the ionic compound sodium chloride. So you write gram formula weight. Formula weight of an ionic compound in grams is gram formula weight, and multiply it with its stoichiometric coefficient 2. So here we would get 2 times. The formula weight of NaCl is 23 plus 35.5, so it is 58.5. Therefore, 1 gram formula weight of NaCl is 58.5 grams of NaCl. So, 2 gram atoms of sodium combine with 1 mole of chlorine to produce 2 gram formula weights of NaCl. And these are the weights of different reactants and products involved in this reaction. I mean the relative weights. Now let us do another example. Let us figure out the weights of carbon and oxygen that completely combine and the weight of carbon dioxide produced in this reaction. First, we have to make sure that the equation is balanced. This equation is balanced. What do we have here? C. This is the symbol of carbon and it represents 1 carbon atom. So we have to write 1 gram atom of carbon multiply it with its stoichiometric coefficient, that is 1. If there is nothing, we have to imagine a 1 there. O2 is the molecular formula of oxygen, so we have to say 1 mole of oxygen and multiply it with its stoichiometric coefficient, and it is again 1. And on this side we have CO2. This is the molecular formula of carbon dioxide, so 1 mole of carbon dioxide and multiply it with its stoichiometric coefficient, which is again 1. So now this line says 1 gram atom of carbon combines with 1 mole of oxygen to produce 1 mole of carbon dioxide. 1 gram atom of carbon is 12 grams of carbon approximately. Atomic weight of carbon is approximately 12. Multiplied with 1 is 12 grams plus 1 mole of oxygen is approximately 32 grams of oxygen. Molecular weight of oxygen is approximately 32, multiplied by 1 is 32 grams. Molecular weight of carbon dioxide is 12 plus 2 times 16. Atomic weight of carbon is 12, atomic weight of oxygen is 16. We have 2 oxygen atoms, so 2 times 16 plus 12, this is 44. So 1 mole of carbon dioxide is 44 grams of carbon dioxide, multiplied by 1 is 44 grams. So we figured out the relative weights of carbon, oxygen and carbon dioxide for this reaction. Let us do another example. This is calcium carbide or calcium acetylide, and it reacts with nitrogen to produce calcium cyanamide and carbon. Calcium carbide is an ionic compound, so we have to say 1 gram formula weight of calcium carbide and multiply it with its stoichiometric coefficient, which is 1, plus N2 is the molecular formula of nitrogen, so we have to say 1 mole of nitrogen, multiply it with its stoichiometric coefficient, which is again 1, produces, this is again an ionic compound, so we have to say 1 gram formula weight of calcium cyanamide and multiply it with its stoichiometric coefficient, plus carbon represents 1 atom of carbon, so 1 gram atom of carbon multiplied with its stoichiometric coefficient, which is 1. The formula weight of calcium carbide is 40 plus 2 times 12. Atomic weight of calcium is approximately 40. Atomic weight of carbon is approximately 12, so 2 carbon atoms there. So 2 times 12 plus 40 is 24 plus 40, is it 64? Yes. So 1 gram formula weight of calcium carbide is 64 grams of calcium carbide multiplied with its stoichiometric coefficient, which is 1, plus atomic weight of nitrogen is 14, so 2 atoms of nitrogen in 1 nitrogen molecule, so molecular weight of nitrogen is 28. So 1 mole of nitrogen would be 28 grams of nitrogen multiplied by 1. Formula weight of calcium cyanamide is 40 plus 12 plus 2 times 14. 28 plus 12 plus 40. Is it 40 plus 40, 80? So 1 gram formula weight of calcium cyanamide would be 80 grams of calcium cyanamide multiplied with its stoichiometric coefficient, plus 1 gram atom of carbon is 12 grams of carbon multiplied with its stoichiometric coefficient. So we again figured out the relative weights of various substances involved in this reaction. Okay, one more example. Liquid ammonia has an unusual power to dissolve metals like sodium. And the solution of sodium in ammonia slowly decomposes to produce an amide with the liberation of hydrogen gas. Let us calculate the relative weights of different substances involved in this reaction. Na represents an atom of sodium, so 1 gram atom of sodium multiplied by its stoichiometric coefficient 2 plus NH3 is the molecular formula of ammonia, so 1 mole of ammonia multiplied by its stoichiometric coefficient. Na plus is a sodium ion, not a sodium atom. So we have to say 1 gram ion of sodium ions multiplied by its stoichiometric coefficient 2. NH2 minus is an amide ion. So it is 1 gram ion of amide ion multiplied by its stoichiometric coefficient 2 plus H2 is the molecular formula of hydrogen, so 1 mole of hydrogen multiplied by 1, that is its stoichiometric coefficient. 1 gram atom of sodium is 23 grams of sodium multiplied by 2 plus 1 mole of ammonia. Atomic weight of nitrogen is 14 and atomic weight of hydrogen is approximately 1. So 3 times 1 plus 14 is 17. So molecular weight of ammonia is 17. So 1 mole of ammonia is 17 grams of ammonia multiplied by 2. What is 1 gram ion of sodium ions? What is the mass of 1 gram ion of sodium ions? See, when a sodium atom changes into a sodium ion, there is very little change in its mass. So we can take the ionic weight of sodium ion same as the atomic weight of sodium. So ionic weight of sodium ion is 23. So 1 gram ion of sodium ion is 23 grams. So 2 times 23 grams of sodium ions plus what is the ionic weight of amide ions? 14 plus 2 times 1, that is 16. So 1 gram ion of amide ions would be 16 grams multiplied by 2 plus molecular weight of hydrogen is 2. So 1 mole of hydrogen is 2 grams of hydrogen multiplied by 1. So here are the relative weights of different reactants and products in this reaction. Now in this reaction, hydrogen gas reacts with chlorine gas to produce hydrogen chloride gas. Again, 1 mole of hydrogen multiplied by 1 plus 1 mole of chlorine multiplied by 1 produce 1 mole of hydrogen chloride multiplied by 2. From this we can easily figure out their relative weights, and I will leave that as an exercise to you. But we know 1 mole of all molecular substances contain the same number of molecules, and we call it Avogadro's number. So 1 mole of hydrogen has an Avogadro's number of hydrogen molecules, 1 mole of chlorine has an Avogadro's number of chlorine molecules, and 1 mole of hydrogen chloride has an Avogadro's number of hydrogen chloride molecules. Now, according to Avogadro's law, if you take equal volumes of different gases at the same temperature and pressure, they contain equal number of molecules, then the converse also must be true, right? If you take equal number of molecules of different gases at the same temperature and pressure, they must have equal volumes. Here, all the reactants and products are at the same temperature and pressure. So, if an Avogadro's number of hydrogen molecules have a volume of V liters, then an Avogadro's number of chlorine molecules must also have a volume of V liters. And an Avogadro's number of hydrogen chloride molecules must also have the same volume. Now this line says V liters of hydrogen combine with V liters of chlorine to produce 2 times V liters of hydrogen chloride. Now if you cancel V throughout, it becomes 1 liter of hydrogen combines with 1 liter of chlorine to produce 2 liters of hydrogen chloride. And if you take the ratio of these volumes, it is 1 to 1 to 2, same as the ratio of their stoichiometric coefficients. So, in a chemical reaction, the ratio of the volumes of gaseous reactants that are combining and the gaseous products that are formed is same as the ratio of their stoichiometric coefficients. So just by looking at this equation, we can tell 1 liter of hydrogen combines with 1 liter of chlorine to produce 2 liters of hydrogen chloride gas, because all these are gases. Remember, this rule is applicable only to gaseous reactants and gaseous products, not for solids or liquids, because Avogadro's law is applicable only to gases. Let us look at another example. 2CO plus O2 produce 2CO2. All are gases. So what can we say about the ratio of the volumes of the reactants and products involved in this reaction? Same as the ratio of their stoichiometric coefficients, right? 2 to 1 to 2. That is 2 liters or 2 volumes of carbon monoxide combine with 1 volume of oxygen to produce 2 volumes of carbon dioxide. So 2 liters of carbon monoxide, 1 liter of oxygen produce 2 liters of carbon dioxide. As we just discussed, according to Avogadro's law, if you take equal volumes of different gases at the same temperature and pressure, they will have equal number of molecules. But looking at helium, you would say it does not contain molecules. That is true. Helium is composed of helium atoms. But we can treat a helium atom as a helium molecule that is composed of only one atom. And we are not violating any rules by treating a helium atom as a monoatomic molecule. So, equal volumes of different gases at the same temperature and pressure contain equal number of molecules. Then the converse also must be true. If you take equal number of molecules of different gases at the same temperature and pressure, they must have equal volumes. And we know 1 mole of any substance, whether it is a solid or a liquid or a gas, contains an Avogadro's number of molecules. So 1 mole of all gases contain the same number of molecules, and that is an Avogadro's number of molecules. So 1 mole of all gases at the same temperature and pressure will have the same volume because they have the same number of molecules. And the volume occupied by 1 mole of a gas is called gram molar volume or gram molecular volume, because mole is also known as gram mole or gram molecule. This name is derived from this name is derived from this. So gram molar volume or gram molecular volume is the volume occupied by 1 mole of any gas. And because 1 mole of all gases contain the same number of molecules, gram molar volume is same for all gases at the same temperature and pressure. Of course, if you change temperature and pressure, gram molar volume also changes. But if you measure the value of gram molar volume at standard temperature and pressure, that is 0 degrees centigrade and 1 bar pressure, its value will be 22.71 liters or 22.71 decimeter cube. Assuming the gas is an ideal gas. We will discuss what an ideal gas is later. But if you measure the volume of 1 mole of a gas at NTP, normal temperature and pressure, that is at 0 degrees centigrade and 1 atmosphere pressure, its value is 22.4 liters. Again, assuming the gas is ideal. Now, the interesting fact with Avogadro's law is the volume of a gas at a given temperature and pressure then only depends on the number of molecules and nothing else. Because if you have equal number of molecules of different gases, they would have the same volume. So it doesn't matter whether the gas is oxygen or methane or helium or chlorine or some other gas. As long as we have the same number of molecules, their volumes are same. See, the relative atomic mass of helium is 4. Relative molecular mass of oxygen is 32 and that of methane is 16. So these molecules have different masses. And here, helium molecule has only 1 atom in it. Oxygen molecule has 2 atoms in it. Methane molecule has altogether 5 atoms in it. Doesn't matter. It depends only on the number of molecules and nothing else. And it could even be a mixture of non-reacting gases. You take a mixture of helium and oxygen that contain the same number of molecules as a sample of methane, then these two samples would have the same volume if the total number of molecules in this mixture is equal to the total number of molecules in methane. It doesn't matter whether it is a single gas or even a mixture of gases. This is very interesting. The volume of a gas at a given temperature and pressure depends only on the number of molecules and nothing else, not on their masses and not on what is present inside these molecules. Of course, assuming that it is an ideal gas.